Hello, welcome to a video discussing section 2.3 on continuity and limits. Hopefully the background noise of the washer, or I think the dryer, I should know that. The dryer running is not bothering me here in my home office, which is actually in the laundry room. Anyway, let's talk about continuity. In pre-calculus, you use an intuitive definition for a function that is continuous over an interval. So we really want to emphasize that phrase, continuous over an interval, as one that can be sketched and in quotations without lifting the pencil from the paper from the beginning to the end of the interval. So for example, let's say I'm focused on this function here in example 1a. My interval is from a to b inclusive. And can I sketch this curve without lifting the pencil off the paper? Well, in this case, my right index finger, can I lift that off the mouse? No, I had to keep my left index finger on the mouse, the left mouse button the whole time to draw that curve. Whereas here, I draw this and then I have to lift my finger and then get to the next part. So there's a break here. So the answer, of course, is yes. We are continuous over an interval, the interval from A to B. Here I'm not continuous because obviously there's a break here, so we say no. How about this one? I draw this curve, but this looks like it's going down forever. Then I gotta lift my finger off the mouse button and draw another curve. Or again, if you're doing this on paper, lifting your pencil off or pen off the paper. So is this continuous on the interval from A to B inclusive? Well, of course not. However, is it continuous on the interval from A to C non-inclusive? So let me go ahead and erase this. So from A to C, so C is actually right in the middle. And non-inclusive, well, yeah, it is continuous there on that interval. So we have to be very mindful about our intervals. So we use the following definition using limits as follows. Or so we refine our definition using limits as follows. A function f of x is continuous at an interior point, x equals c. So for example, you consider that to be an interior point, if you like, if and only if the following are true. F of c exists. Does f of c exist here? Well, yeah. I know the y value at x equals c. That's what this means, that first condition. So we have to satisfy these three conditions here. So can I find the y value at x equals c? Yes. So we'll look at 1a again. Well, the limit exists as x approaches c. So basically, does the LHL equal the RHL? So remember, the LHL is x approaches c from the left, RHL x approaches c from the right. If those are equal, will the limit exist? Sure. And of course, that is true for example 1a as well. And then finally, conditions 1 and 2, those outcomes, the limit that we get as x approaches c, the y value we get when we plug in x equals c into the function, are those the same thing? If you get yes again, then we have continuity. Let me give you some examples where that may not work, and we'll see that for sure later in these notes. Remember we did something like this, I think it's section 2.1, we had a linear function, then we had a hole here, then we kept this going, and then the dot was out here somewhere, right? So f of c was right there. Now our limit did exist as we went from left to right. So we did satisfy the first two conditions. However, f of c did not equal the limit. So, and I had to actually lift my pencil or pen or my left, my finger off the left mouse button to keep that curve going. So in this case, this will be no, because we do see a break in the graph. And of course, like example B is also no. And example C for this interval is also no. So you have to make sure that, hey, can you define f of c? Does the limit exist as x approaches c? So left hand limit equals right hand limit. And of course, do the limit and f of c equal each other? When we're dealing with one-sided limits, if we're dealing with an endpoint, like if I want to see if this is a continuous at x equals a, for example, or x equals b, then just use an appropriate one-sided limit, because you won't have an LHL or an RHL to both look at. You can only have one or the other. But that's still okay. You could still say, for example, 1a, it is continuous here or it is continuous here, because you can use the appropriate one-side limit for either of those cases. So this box is extremely important for continuity, and we're going to continue looking at that often. Okay, let's look at the bottom of page 1. This is example 1 here. Actually, sorry, that's a typo. That should be example 2, but we'll call it the second example 1. How about that? So we got a square root function, root x plus 5 plus 1. Well, hopefully you know that the domain is from -5 to infinity. So we are going to draw -5, 1, sorry. If I plug in -5 for x, make a little table. -5, 1. If I plug in -4, I get 2. If I plug in -1, I get 3. And the graph looks like that. So I have my domain, I have my graph. Show that f is continuous at x equals -1. So here's x equals -1. So we go through 3 conditions. Sorry, I'm taking up some of the space here for C. Does f of -1 exist? Well, yeah, totally. Plug in -1. It's fine. You get an answer. I got one right here. Does the limit as x approaches -1 of f of x exist? Well, let's find my LHL. The limit as x approaches -1 from the left. Well, of course it does. If I go from -1 from the left, I'm getting closer to 3 here. How about my RHL? My limit as x approaches -1 from the right of f of x. Sorry for the messy handwriting. Well, yeah, if I'm coming from the right, it's also getting closer to 3. And they equal each other. So of course the limit exists. The two-sided limit is fine. And are these the same? Does f of -1 equal the limit as x approaches -1 of f of x? Well, duh. Yeah, that's 3. That limit was 3. So check again. So the answer is yes, it is continuous, and we showed that correctly. So that's example 1b. You go through the same process again for 1c. Let me clear that up. So, does f of -5 exist? So now we're doing c, by the way. Yeah, of course it does. I know it's 1, right from my table that I just did, and my graph as well. Let me replicate the graph again. Sorry about that. Now, does the limit exist as x approaches -5 of f of x? Yes, again. Of course it does. Excuse me. Of course it does, because if I do the appropriate one-side limit, even though -5 is an endpoint, all I have to just do is do the RHL from the right side. That does exist. As I get closer to -5 from the right side, we see it's approaching 1. So yeah, totally. And then finally, do these equal each other? Well, they both equal 1. So yeah, of course. So you go through all 3 of those conditions. I'm going to beat that into you guys over and over again. Sorry for using a word like that. But yeah, I have to make sure you guys know this so well. It's very, very important. Okay. For D. And again, just to recap, again, does f of c exist? Does the limit as x approaches c of f of x exist? And does the limit equal f of c? Those 3 things must happen to have continuity. So B and C, we showed it by just going through those 3 things in our checklist. Finding points of discontinuity. Actually, we don't have any. There are none. Now, yes, it's not defined. For x less than -5. We know this. This is not defined for x less than -5. 100% we know this. But the thing is that when you want continuity, you need to make sure these things are happening in your domain. So I should have emphasized that a little earlier. In your domain. What is our domain here? -5 to infinity. So in our domain, do we have any issues at all? We did not. So we could say this is continuous on its domain, totally. Now we will look at things that are not continuous. That will be mainly piecewise functions, and maybe some other kind of functions that are a little funky. But for the most part, this is continuous. Even though it's not defined for x less than -5, we're not looking at anything less than -5. We're only focusing on our domain. In our domain, this is continuous. Because I can draw that very smoothly without any breaks in it. And then finally, is it a continuous function? The answer is yes, it is. We say yes, and be clear about this continuous on its domain, which of course is from -5 to infinity. Okay, so definitions. And actually I'll stop the video right now.